Hi everyone. In this lecture, we're going to discuss about basic electrical properties of MOSFET. That is, electrical properties related to the current, IDS, okay, and the threshold voltage and the body effect of the MOS transistor. Okay, here they have given different regions of operation of MOS transistor, cutoff region, non-saturation, and for each region of operation you're going to have different IDS equation. We'll see that what is cutoff and what is non-saturation, what is saturation region. Then we have channel length modulation, that is the length of the channel varies with respect to applied VDS. We'll see that in detail. And then we have drain resistance, transconductance EM, body effect, the threshold voltage, the minimum voltage required to on the transistor. Then we have pull up to pull down ratios of the impedance, that is length to width ratios of the channel length, and different pull up of the inverters. Then figure of merit, if possible small signal model of MOSFET. These are the electrical properties of a MOSFET. Okay, so first I'll explain the region of operation of MOS transistor, then we'll see the equation for IDS versus VDS, that is current and drain resistance, current IDS versus VDS, voltage applied VDS. So three regions operations we are going to have for a transistor. First is cutoff, that is the transistor NMOS or PMOS. In this region of operation, cutoff region, it is going to just act as open switch, no current flows. This is, if we have this NMOS transistor, we take NMOS transistor, we have here P substrate and here we have the gate. Okay, this is thin oxide. We try to understand the operation of the NMOS, operating principle of NMOS, the source, drain, and this is going to be the gate. Okay, source, gate, drain we're going to have. Now this source is generally connected to the fourth terminal P substrate and it is at the ground level potential, 0 voltage. Now the gate voltage, it is connected positive voltage, the negative terminal is connected to ground. And here we have VGS, gate to source voltage. Similarly you're going to have VDS, this is negative terminal connected to again ground terminal, and this is VDS, drain to source voltage. How the operation, as I said here, you are going to have three regions of operation: cutoff, non-saturation and saturation region of operation. Here first we'll see cutoff region where we have IDS is equal to 0. So what is the cutoff? Means whenever the gate to source voltage is less than the threshold voltage. What is the threshold voltage here? VTH is the minimum gate to source voltage required to on the transistor. That is the minimum gate to source voltage required to form the channel between source and drain is called the threshold voltage VTH. If the applied gate to source voltage VGS is less than the threshold voltage VTH, then the transistor operates in off, that is cutoff region. IDS is almost equal to 0 and we say that is off switch. Next for non-saturation region, that is resistive region also it is called. So whenever we have VGS, the gate to source voltage, greater than or equal to or greater than threshold voltage, so the positive voltage is applied at the gate terminals. So the minority carriers of the P substrate electrons will come between source and drain and form as a channel. Okay, before we apply this VGS greater than VTH, or you can see here you're going to have this depletion region between N plus and P substrate. This is if you apply VGS greater than VTH, or VGS less than VTH, or if you apply VGS is equal to 0, for even all the voltages you are going to have depletion region, this one between N plus and P substrate. Between N plus and P substrate you are going to have the depletion region. Okay. Now VGS less than VTH, first cutoff region, or you can even say it is VGS equal to 0 or VGS less than VTH, that is the first region of operation. Second region of operation where we have VGS greater than VTH. Once we apply positive voltage greater than VTH, the minority carriers of P substrate attracts and form as a channel between source and drain, and it is a channel is going to be formed between source and drain. Like you have a river, two sides of the river you have, two sides of a canal you have, two sides, and if you want to cross from one side to another side of the river or canal, you're going to have a bridge. Similarly here, for the electrons to move from source to drain, the channel is formed. Through this channel electrons are going to start moving. Now once we apply VGS greater than VTH, channel is formed. Now when we apply VDS, now this also positive voltage applied to the drain, that is reverse bias to the drain, because drain is of N plus type, as we have discussed in earlier video. Source is also N plus, drain is also N plus type. Now we are applying positive VDS to N plus, so it is reverse biased, and the depletion region slightly increases because of this positive VDS. And the VDS now we applied in the second region of operation greater than 0, electron starts moving towards the drain. Electrons starts moving towards the drain, and we get the conventional current flow as IDS. IDS comes into picture. Electrons move from source to drain and we get the current IDS. Okay. In cutoff region IDS is equal to 0. Now in the non-saturation region IDS is not equal to 0, and we have an equation for this IDS. We'll just see how the equation we are going to get for non-saturation as well as for third region also how we get, we'll see. Now this is the second region of operation. For the third region of operation, further VGS is greater than or equal to VTH, that is okay, and this is vertical voltage is applied, and we are going to apply VDS in the second region also greater than 0. Now VDS is going on increasing. We are going to increase VDS, power supply voltage, we are going to going on increase. Whenever this VDS is greater than or equal to, whenever this VDS is greater than or equal to the voltage VGS minus VTH. What is VGS minus VTH? We applied VGS greater than VTH, and out of VGS, VTH is utilized to form the channel. So suppose if you apply 3 volts at the gate to source voltage, 1 volt is utilized to form the channel. So VGS minus VTH is nothing but 3 minus 1, that is going to be 2 volts. So that is nothing but VGS minus VTH, which is called as the effective gate voltage. So whenever the VDS which we are increasing reaches to a voltage greater than or equal to VGS minus VTH, then very high current flows. IDS will be IDS saturation, and that current will be almost constant. Okay, and the depletion region here which we have near the drain, it is going on increasing. So when we apply VDS greater than 0, it will increase such that the channel near the drain is going to pinch off. Channel will not be present because of increase of the depletion region here. The channel is pinched off near the drain. But how we can say that the channel is not present? But we are saying that the current IDS is going to be the highest current, which is the saturation current. IDS will be highest in this region, which is almost constant. It is like you are watching a bike race. Okay, you are sitting and watching a bike race. Somebody is moving with a 200 kilometers per hour from your front. The bike crossed already, but we are unable to see because it is so fast that he's crossed from our front. We are unable to see him. We see him, but we are unable to observe. So fast it is. Similarly, electron crosses the depletion region, enters into drain. Electrons crosses the depletion region, very high number of electrons enters into drain, and IDS will be maximum. Why? Because VDS which is applied is high, the channel length here is very small, not even micrometers, it will be nanometers. So even 2 volts or 1.5 volts, it will give very high electric field. Okay, very high electric field will be there because of VDS by the channel length. So the electrons moves very fast, crossing the depletion region, enters into the drain. So this is called as transverse electric field. When we have transverse and longitudinal electric field, about this we'll see in later classes. Okay, vertical you have because of VGS, that is perpendicular, that is called as transverse electric field. Along the channel you applied VDS, that is called as horizontal electric field. Because of that, electrons moves towards the drain. Vertical because of VGS, that is called as transverse electric field. Okay, these are the three regions of operation we have: cutoff region, non-saturation region, and saturation region. We'll see how the equations we get for this IDS current. Okay, so drain test, these all we see one by one. So here we have the derivation which derives the relation between IDS equation with respect to voltages. Since here we have VGS applied to form the channel and VDS is applied for moving the electrons. So current IDS depends on these two voltages, VGS as well as VDS both. Okay, so IDS is a function of VGS, VDS threshold voltage, and the parameters like width of the channel length of the channel, we'll see what they are. So all these parameters affect the drain IDS current, drain to source current. Okay, right. So we'll see the equation now. Here it is given what the threshold voltage VT or VTH, drain to source voltage, gate to source voltage, gate to drain voltage, and mobility of electrons given by mu n, and mobility of holes given by mu p, and mu n is almost greater than or equal to 2.5 times of mu p. That is, mobility of electrons is higher than the mobility of holes by factor of 2.5 times. Okay, next we have thickness of oxide above the gate, thin oxide it is. Then we have epsilon naught, absolute permittivity, then relative permittivity. Then we have electric field across drain to source. This is because of VDS which is applied. This is because of VDS applied longitudinal field. And then we have EG, electric field across gate to channel. This is transverse electric field. This is transverse electric field which is vertical we have because of the VG. VG is nothing but VGS minus VT, HR VT, threshold voltage. Because of VG by thickness of oxide gives this vertical field, transverse electric field we are going to have because of EG. That is because of VGS. Next we have the oxide capacitance C0, capacitance per area. Okay, gate capacitance per area CG. Okay, now this is the important diagram which you have to practice whenever they ask IDS versus VDS equation. Derive the IDS versus VDS equation for different regions of operation. You are going to draw this rectangle, then I will draw here. It is already there. You can see. So what here we have is this is the channel length L, and this is the W, width of the channel. Okay, this how also you can take width of the channel. This is the length of the channel. Here you have drain, it is given. D is the thickness of oxide. This is source and this is drain. Okay, and this is our gate. So whenever we apply VGS here, that is VGS is applied to the gate terminal, that is negative to the source and positive to the gate. The channel is found between source and drain. Okay, that we have seen already the operation. Now here IDS, we know that current I is nothing but charge by time. So IDS current, drain to source current, even you can write minus ISDS, charge induced in the channel divided by the transit time. Transit time is the time taken by the electrons to move from source to drain, is called as transit time or electron transit time. Okay, that is tau. So IDS is equal to QL by tau, charge induced in the channel divided by electron transit time. Now we have two steps in deriving the equation for IDS. First, step 1, where we are going to calculate the tau transit time, that is tau SD, time taken by the electrons to move from source to drain, that is channel length divided by the velocity. Length by velocity gives the time. Okay, now we have the velocity V is equal to mu into EDS. Velocity V is equal to mu into EDS. EDS is because of applied drain to source voltage, and that EDS is nothing but VDS by L. Okay, that is equal to VDS by L. I think you are getting here. EDS is the field due to applied drain to source voltage along the channel. So EDS is the electric field, which is nothing but voltage by length. Voltage by length. And velocity of the electrons is mu into EDS. Mobility into EDS, electric field intensity. And EDS is nothing but voltage by length of the channel. Right, that is equation number 5. Next we have tau, that is equation number 2. We are going to substitute this equation number 5. So what we have, length by velocity, what we have, tau SD is equal to length by velocity. Distance by velocity gives the time. So length we keep it as same, and in the velocity here we substitute mu into VDS by L. Mu into VDS by L. This L goes into the numerator. We get L square by mu VDS. So tau SD we get it as L square by mu VDS. This is the first case or first step, not case, first step of deriving the IDS equation. What we got? The denominator of IDS we got, that is transit time tau SD equation, L square by mu ds. Simple. Tau is length by velocity, velocity is mu into EDS, and EDS is nothing but voltage by length. These two we substituted in equation number 2. We get L square by mu VDS. L is the channel length, mu is the mobility, VDS the drain to source voltage applied. Right. Next we are going to calculate what is QC, charge induced in the channel, which is the numerator of the IDS. Tau SD is the denominator of IDS. QC, charge induced in the channel, is the numerator of IDS. So we have seen just now, again I'll draw this n plus, and here you, this is P substrate. You're going to even have the depletion region. Here you're going to have the channel is formed. The amount of charge what is here in the channel, that is QC, charge induced in the channel. We know that charge induced in the channel is epsilon A into E. How we got this epsilon? Q equal to CV, I think Q charge is equal to C into V, charge. and C capacitance is nothing but epsilon in epsilon A by D. Epsilon A by D is nothing but capacitance into voltage. Now this voltage divided by this thickness gives the field. D is the thickness of oxide. So we get here V by D is the field. V by D is the field Eg, and epsilon, in place of epsilon we can write relative permittivity, that is epsilon ins of the insulator, and epsilon naught absolute permittivity. And in place of area A, that is area of the channel, we write it as W into L, width of the channel into length of the channel. That's how we got this QC is equal to epsilon ins epsilon naught WL into Eg. Right. Now here we have what is Eg. Now you have to calculate. Epsilon ns is constant, epsilon naught is constant, W is constant, L is constant, because width of the channel is fixed, length of the channel is fixed. So we have to what here calculate is Eg. Okay, Eg is the field due to gate to source voltage. So here VGS is applied. Out of VGS applied, VTH is utilized to form the channel. So effective gate voltage which is present, VG, is nothing but VGS minus VT or VTH. So that is applied here vertically, that is transverse field. And now here along the channel, here we have applied VDS. So if we consider the linear region, an average voltage drop across this channel length L, the average voltage drop we take it as VDS by 2. It is going to be VDS by 2. So the potential difference across the gate and the channel is VG minus VDS by 2, this divided by D. If you take, that gives the field. Okay, VG is nothing but VGS minus VT minus VDS divided by D. If you take, that gives the effective gate field Eg. The potential difference is Vg minus VDS by 2 divided by the thickness of oxide gives the field Eg. So Eg is the effective gate field because of VGS, and VDS also along this drop, average voltage drop across the channel length, VDS by 2. So we have VGS minus VT, that is for Vg, minus VDS by 2 whole divided by thickness of oxide. This gives the Eg. This if you are able to do now from here onwards. Now what we are going to do, in the place of Eg, that is equation 8 is substituted in equation 7. Equation 8 is substituted in equation 7. So we got QC is epsilon ins epsilon naught WL by D into VGS minus VT minus VDS by 2. Now this QC and earlier we got tau SD, both will be substituted in ISD equation. Okay, so this QC comes in the numerator. QC where we get in the numerator we got, and the tau SD just now we have seen, that is L square by mu VDS, that comes in the denominator. Right. So here we have, now this D comes into the denominator, this L is in the numerator, 1L and L square, 1L will get cancelled. Okay, this mu VDS goes into the numerator. We have VGS minus VT minus VDS by 2. Okay, epsilon ins epsilon naught W, they come in the numerator itself. So in the next step we'll see, here we get the equation. So this is epsilon ins epsilon naught, D comes in the numerator, and mu mobility of the carriers, W is present, L is present. This Vd which comes in the numerator, that is multiplied for both the terms. So we get VDS minus into VGS minus VT into VDS minus VDS square by 2. Okay, right. So now this epsilon ins epsilon naught by D can be replaced with K. It's a constant, it is replaced with K. So this equation here, given equation 11 itself, gives the current equation in non-saturation region. Or if you replace this epsilon minus epsilon naught by D with K, this is process transconductance, it is K, it is called. You can write that also, K into W by L into this, that is equation number 12. Or this K into W by L can be replaced with beta. This K into W by L can be replaced with beta, which is called as device process. K is process transconductance, beta is the device transconductance beta. Okay, anything you can write. And even this epsilon minus epsilon naught by D can be replaced with C naught, capacitance per gate area, C naught, which you have seen earlier. It is replaced with C naught also, right? Now these are the equations for non-saturation region operation. Now when we go for saturation region, as we are going on increasing the VDS, whenever VDS is equal to or greater than VGS minus VTH, the limiting case here is VGS minus VT or VTH. Whenever the VDS is equal to this VGS minus VT, the transistor enters into saturation region. And what we have to do here is, this VDS can be replaced with VGS minus VTH. This VDS is replaced with VGS minus VTH. So here we get, this will become VGS minus VTH into another VGS minus VTH, that is give square, minus VGS minus VTH or VT square by 2. So this is, it is like 1 minus 1 by 2, VGS minus VT square minus VGS minus VT square by 2 means 1 minus 1 by 2, it is just 1 by 2, that is VGS minus VT square by 2. So this is the equation for saturation region operation. So we got two equations, one is for non-saturation region operation, another is for saturation region operation. And for cutoff region, IDS is equal to 0. Okay, so these are the two equations which relates IDS and VDS. And problems also, it will be, they'll ask, we'll discuss the problems also in coming videos. And here, channel length modulation. What is channel length modulation? Here is, we have this N plus, here we have N plus, and here we have thin oxide gate, that is polysilicon. Here we have the depletion region, here also we have the depletion region. Here we are applying VDS. So whenever we going on increasing VDS, this depletion region is going to increase, and the channel is formed earlier because VGS is greater than VTS, channel is formed. Because of increasing of this depletion region, which is due to increase of VDS, the channel length is going on decrease. Channel length is going on decrease. Earlier it is like this square rectangle shape. Now it is going to first like this, and then further the channel length is going on decreasing with the increase of the depletion region. So what is happening here? The length of the channel is modified with respect to the applied VDS voltage. That is called as channel length modulation. Okay, so this channel length modulation can also be included in the current equation. Equation 14 is, which we have done already, 1 by 2 k W by L into VGS minus VTS square. Now this channel length modulation, if it is included in this, that is length is modified, going on decreasing with the change in the length with increase of VDS. Suppose if you take delta L, so L minus delta L we can take. So W by L we are taken common from the denominator. So what we get? W by L common. So 1 minus delta L by L we get. Okay. This delta L by L is very small here, because that change in channel length is very small. Okay, so 1 minus delta L whole to the power of, so when we take this in the numerator, it is there in the denominator, 1 by delta L by L, it is there in the denominator. When we take in the numerator, it becomes as 1 minus delta L by L whole to the power of minus 1. So we have the expansion theorem here. So when we expand this, 1 minus delta L by L, this becomes plus, and then further terms whichever are delta L square by L square, that is further small. So higher degree, second, third order are neglected, only the first order delta L by L is considered. Okay, so in place of 1 by 1 minus delta L by L is replaced with 1 plus delta L by L only. Now if you multiply this, that is VGS, here we have, and delta L here we take it as lambda into VDS. By definition it is, where lambda is called as channel length modulation factor. Okay, so here we get 1 plus lambda dash by L. Lambda dash you can take it as lambda also, channel length modulation factor, into VDS we have. So finally what is important here is this equation K into W by L into VGS minus VT square by 2 is the saturation current equation. Extra what we got here is lambda dash by L into VDS. This lambda dash by L is taken as lambda, that is process technology depends, it depends on the process technology. Okay, channel length how it is going to modify. So 1 plus lambda into VDS. So here main important thing what you have to remember is what is channel length modulation, that is the length of the channel is going to be modified with respect to the applied VDS, right? So again this IDS equal to 0, that is cutoff region, we have already discussed. Whenever VGS less than VTH and VDS is equal to 0, no channel exists, no current flows, and IDS is equal to 0. Non-saturation region we have seen whenever VGS greater than VTH and VDS is less than VGS minus VTH. Here it is not equal to, it is less than VGS minus VT or VTH, less than. Okay, right, but VDS is greater than 0. This is the second region of operation. Next we have, already it is explained, saturation region also we got. Channel length modulation, these brief like equations they are given here. 1 plus lambda Vs included for considering the channel length modulation factor, right? Now next, this is about the IDS versus VDS and channel length modulation factor also we have discussed. Next we have drain resistance, RDS. RDS, drain resistance, is obviously voltage by current, so it is VDS by IDS. The condition but here is applied VGS is equal to 0, that is when the transistor is off, then only we can calculate this drain resistance RDS. Okay, but here don't confuse here, that is very small VGS you can consider, not small VGS. Here RDS we get VDS by IDS. This VGS by definition it is VGS is equal to 0, but IDS is going to be replaced with the linear current equation. IDS is replaced with linear current equation, approximately non-saturation region of operation. For definition of drain resistance, we take VGS is equal to 0. Okay, but here we are going to consider it as linear region or non-saturation region current, right? But the condition here it is VDS is very small, VDS is very small and VDS square is further very small. So this VDS square by 2 in the denominator is neglected. So what we left is K into W by L into VGS minus VT into VDS. Then this VDS got cancelled. So drain resistance RDS is 1 by K into W by L into VGS minus VT. Okay, so this is the drain resistance equation. Here you should not confuse that here we have taken VGS equal to 0 and channel is not formed. Even then it is taken, the IDS is non-saturation region equation. Yes, for the definition of VGS is taken as 0 for drain resistance definition, but we take for the calculation purpose we consider that IDS is small. Okay, non-saturation region means IDS is small, so that small IDS equation we are going to take, which is for non-saturation region equation, right? So we got this RDS is K into W by L. If you take VGS minus VT in the numerator, we get it as minus 1 for non-saturation region only, right? Next we have RDS in, if you consider channel length modulation factor also, here also by definition VGS is equal to 0. Theoretically it is VGS equal to 0, don't worry. Why then you are taking IDS as an equation of non-saturation? Theoretically many things will be there, but when it comes to the practical we can't have the solution until unless we do some assumptions. Okay, RS it is equal to 1 by IDS, and that is RDS is 1 by lambda IDS, that is drain to source resistance when we consider the channel length modulation. Okay, now here thus 1 by RDS is equal to GDS, that is drain conductance it is. Okay, and output conductance also it is called as GDS or output conductance it is called. RS is equal to 1 by IDS, RDS is equal to 1 by lambda IDS here we have. Okay, since if you substitute here idea in place of drain to source resistance 1 by lambda IDS by definition channel length modulation, and the GDS is nothing but 1 by RDS, so we get GDS output conductance is equal to lambda into IDS, right? Next we have transconductance GM, which is nothing but channel that is the current ID, drain current, drain to source current ID by gate to source voltage. So transconductance relates output and input. Transconductance relates output current, that is change in the output current by divided by the change in the input voltage, that is from how much change in input we are getting the change in the output current. The ratio of change output current by when we have the change in input voltage gives the transconductance GM. So here to calculate the transconductance we take the saturation region equation of IDS, which is nothing but K into W by L into VGS minus VT square by 2. Okay, so here when we substitute this IDS and VGS, we are going to do the IDS equal to mu into COX, that is capacitance per area into W by L, VGS minus VT square by 2. If we differentiate with respect to VGS both sides, dou IDS by dou VGS, we get dou ID, this is also dou IDS by dou VDS. So what we get, this mu into COX into W by L, it will be same, differentiating with respect to VGS, so we get 2 into VGS minus VT, this 2 will get cancelled, and here we have Wn, here it is Wn, it is nothing but width of the channel length, N represents for NMOS. Okay, L is the channel length. So the definition of transconductance is Wn into COX capacitance, C suffix OX into W by L into VGS minus VT. This for conductance equation for transconductance GM. Okay, here the equation which is used is saturation current equation, differentiated with respect to VGS. Dou IDS by change, it is change of output by change of input voltage. Whereas output conductance, which we have seen, the output resistance RDS, that relates, there we use the non-saturation current equation. Okay, express GM with respect to ID. So V effective is nothing but VGS minus VT. V effective, earlier in the derivation of IDS VDS we have seen, V effective is nothing but VG, which is VGS minus VT. So VGS minus VT can be replaced with effective voltage. If you do the cross multiplication here, this 2 goes into the numerator of the left hand side, 2ID divided by Wn, width of the NMOS transistor, COX into W by L. Right. Here we have this, we can write it as GM is equal to, here we transconductance it is given, here we have, okay, this mu1, here it is written as W1, this is the width of the channel, mu1 is the mobility, this is mu1, this mistake it was written, mu1 is the mobility of the electrons. Mu1 already it is there in the definition of K includes epsilon naught, epsilon is mu by D, mu into COX into W by, this is also equation for the IDS. So this mu1 is the mobility of electron, that is W, here it is the width of the channel. Okay, it is not W or omega n, it is mu1. So finally we have in all mu1, it is written here W1, it is basically mobility of electrons mu1. So if in terms of effective voltage we got root 2ID by mu1 into COX into W by L. So GM transconductance we get. Now express this GM in terms of effective voltage in ID. Just now we have seen, again this is mu1 only, that is mobility of electrons. So cross multiply, same thing again it is given here. GM is the transconductance. Of simplifying, we have this V effective is VGS minus VT, bringing on the left hand side, 2 goes into the numerator, 2ID by V effective square we have. Now this mu1 into COX into WL is nothing but we have GM, earlier we have seen, so if you substitute there, so we get transconductance GM is equal to 2ID into V effective, that is VGS minus VT by V effective square, 1 V effective VGS minus V effective 1 will get cancelled. Okay, it is written not needed for exams. It is not so important for exams, but you have to just have an idea. Next we have the topic figure of merit. What is figure of merit? Is a quantity needed for giving the performance of any device that is related to the device. Figure of merit is considered. Okay, so it can be related to a particular material or device, NMOS, PMOS or CMOS. You're going to have figure of merit FOG, which is nothing but omega naught, that is frequency response, it is related to omega naught frequency, is equal to GM by CGS. So figure of merit of a device, it is given by transconductance divided by the gate capacitance of the device. Omega naught is equal to GM by CGS. Okay, now I think it is clear. Till now we have discussed IDS versus VDS, the relation and the operation of NMOS transistors, 3 regions of operation of NMOS transistor, then IDS versus VDS equation we have seen. Then we have discussed about output conductance, that is drain resistance, and we got the channel length modulation factor in that also. And next we have seen just now, that is the relation of, between GM CHN figure of merit omega naught. These are the topics which I have discussed till now. Further, next we have the threshold voltage definition and its equation. Already I have told you what is threshold voltage. Threshold voltage is defined as the minimum gate to source voltage required to on the channel. Minimum gate to source voltage required to on the channel, that is called as the threshold voltage. Minimum gate to source voltage to form the channel between source and drain. So by definition of the threshold voltage, you have to remember this equation. Threshold voltage is equal to 5 ms QB minus QSS by C naught, okay, plus 2 into integral, this is a function here, work done function, one by one it is defined here. Q, here we have threshold voltage Vt, which is a function of bulk charges and the surface to surface charge density. I'll tell you where it is, and this is C naught, capacitance, and Fn, okay. So I'll tell you first what is QB here. Again you need to have this NMOS transistor equation, NMOS transistor equation. So here itself we get what is QB and what is QSS. So here whenever the gate to source voltage is applied greater than 0, suppose we start with 0, then 0.5 volts, 1 volt. So whenever it is greater than 0, the minority carriers of electrons are going to attract and they are going to start forming the channel between source and drain. And here you are going to have the immobile negative ions will form initially. Immobile negative ions are going to form initially before the channel is going to form whenever we start applying VGS. These negative immobile are bulk, that's why that is given QB, okay. The charge per unit area in the depletion region, here you are going to have area beneath the oxide. So these are immobile bulky ions, that's why QB is the bulk charge, okay, beneath the oxide. Initially before the channel is formed they come. So that's why these negative charges, what they do, they repel the electrons downwards. So the required VGS is going to increase because of the presence of this negative immobile ions. So that's why that is included in the numerator QB. And this 5ms is the work function between gate and silicon. Work function between gate and silicon. Silicon is nothing but P substrate, that is to take the electrons, the work done in moving the electrons from silicon to the gate area, that is called as the work function between gate and silicon. Now coming to QSS, this is the surface to surface charge density, that is the charge density between in the silicon dioxide. Whenever we apply VGS greater than VTS, channel is formed. Because of this high voltage of VGS, some of the electrons are going to trap in the silicon dioxide polysilicon region or inside the silicon dioxide itself. Some of the electrons are trapped. Now we switch on the switch off the NMOS transistor, work is stopped. Again when we want to switch on the transistor, these electrons already trapped at the interface of this silicon dioxide in the gate interface, or silicon dioxide and P substrate interface. You're going to trapped electrons will be there inside the silicon dioxide also. So those electrons also try to repel the electrons which are coming towards the channel. So this also increases the required that is the threshold voltage required is going to decrease here, QB minus QSS by C naught. So this is trapped electrons, and 5ms is the work function between gate and silicon. Next here we have 5Fn. Fn is the nothing but Fermi level potential between inverted surface and bulk silicon. Inverted surface here is the channel region between source and drain, because earlier it is P type complete, Now once we apply the VGS, the P substrate region between source and drain, from P to it is becoming N type, that is channel. So that is why it is called as the inverted surface. Inverted surface, that is the channel region. So Fermi level potential between inverted surface and the bulk silicon, that is nothing but 5Fn. The values are given 1.5 to 8 into 10 to the power of minus 8 coulombs per meter square. It is C naught is the capacitance per unit gate area. So if they ask in the exam, define threshold voltage and derive the equation for threshold voltage, what you have to do first is define threshold voltage. What I have said, minimum gate to source voltage required to form the channel between source and drain, the minimum voltage required to force the majority characteristics to form the channel, minority carriers here, minority carriers to form the channel between source and drain, that is called as the threshold voltage. And this equation you write and you define one by one. What is QB? Bulk charges, trapped charges, C naught is the capacitance, phi m is the work function, phi n is also the work function. If you define one by one, that is enough for threshold voltage. Now another topic related to threshold voltage itself we have is body effect. What is body effect? Generally the source and the fourth terminal are connected and it is at ground potential, that is 0, substrate, body or bulk and source. But because of the external temperature, we are going to have some electrons which are going to move randomly in the P substrate, and that electrons whenever they increase, that gives rise to some flow of current inside the substrate, and this P substrate itself gives some distributed resistance here. So this resistance into this current due to movement of electrons because of external temperature increase or radiation, we are going to have a source to bulk voltage which should not be there, but because of some extreme circumstances VSB can come into picture. What happens because of VSB? This VSB is positive, negative. Positive voltage is applied to the source. This unwanted voltage, because of extreme circumstances, this can happen, this can present, come into picture. So this positive voltage try to attract the electrons towards the source, whereas the applied VDS try to move the electrons towards the drain, and the gate voltage try to hold the electrons in the channel. But this VSB source to bulk voltage tries to move the electrons towards the source, which disturbs the channel. So the required threshold voltage is going to increase because of this body effect. Why it is called as body effect? Because of the P substrate body only the VSB voltage is generated, or it formed here VSB. That's why it is called as body effect and body effect voltage. So what we are going to do in the threshold voltage equation, when we don't consider the body effect, the threshold voltage is Vt0. When we consider the threshold voltage, we are going to include these two terms here, square root of root 2 phi f and Vsb also included in the threshold voltage. This is the modified equation for the threshold voltage. No need to go in depth here how we got this equation. Only if you remember that equation, Vsb is the bias voltage which we got here. Okay. This gamma is fabrication process parameter you're going to have. And in VSB is equal to 0, when VSB is equal to 0, threshold voltage Vt is equal to Vt0. Okay. Now for NMOS transistor, this threshold voltage is going to be positive, and for PMOS transistor this threshold voltage is going to be negative. Okay. PMOS operation also I'll explain here. It is like you're going to have P plus, you're going to have P plus, here you're going to have N substrate, here you're going to have the thin oxide and polysilicon is formed. This is source, this is drain, and this is gate. So here the minority carriers of N substrate are holes. So whenever VGS applied, For PMOS, this is for PMOS. So negative voltage when it is applied here, negative gate to source voltage is applied. So the minority carriers of N substrate holes, they form as the channel between source and drain. And when we apply the VDS also negative voltage, this hole starts moving towards the drain, and that gives rise to the IDS current, that is because of holes. You can write IDS negative or ISD positive. Okay, so this is because of the holes which are moving from source to drain. So the operation of this is similar to your NMOS. The difference is, in case of NMOS you are going to apply positive gate to source voltage, whereas in case of PMOS you are going to apply negative gate to source voltage and negative VDS, and threshold voltage is also going to be negative. So this is about the operation of NMOS, PMOS, and IDS versus VDS. We have seen figure of merit, we have seen body effect, we have seen, we have discussed these topics. Thank you for watching. We'll continue in the next video.